Hello, my name is Dhanens, and my project is efficient HVAC design in Helena, Montana. This system is being designed for a hypothetical office building to be constructed in Helena. The building would house approximately 55 workers with 4 private offices and a large open office space with cubicles. The building needs a complete heating, ventilation, and air conditioning, or HVAC, system. This includes a boiler and its associated hot water system, an air handling unit, or AHU, and its associated ductwork, and a cooling system. The owner has also requested a recommendation for 6 or 12 south-facing windows, and that a solar wall be implemented into the design. This is the layout of the building. Across the top, you can see the 4 private offices, as well as a break room and the restrooms. In the open office space, you can see 4 sets of cubicles, and on the right side of the building, there's the mechanical room. On the bottom of the mechanical room, you can see the outline for the solar wall. The solar wall is a large sheet of darkly colored metal that is perforated. Air is drawn through the perforated metal, which is heated by the sun, and so the air is heated before it enters the building. This reduces the amount of work that the air handling unit has to do. The occupied design temperature for the building is 72 heating and 75 cooling, and the unoccupied design temperatures are 64 heating and 82 cooling. The building adheres to the International Energy Conservation Code, which provides insulation R values, and also adheres to ASHRAE 62.1, which provides the minimum ventilation requirements. The building will also be able to operate at the maximum and minimum outside design temperatures according to ASHRAE 90.1. For this region, the maximum outside temperature is 90.5 degrees and the minimum is minus 12.5 degrees. Design constraints for this building include the additional heating and cooling load due to added windows, if the 12-window option is used over the 6-window option, the solar wall, which requires additional ductwork and control systems and complicates the control sequence, and the physical design constraints. There's only 3 feet of plenum space, which is a space between the top of the ceiling tiles and the bottom of the roof, which means that there's less room to run ductwork. 2 types of air handling units were analyzed for this system, a constant volume and a variable volume. A constant volume system, as it implies, provides a constant amount of circulating air. It's inexpensive and simple, but it's not very efficient because the fans run at full speed the whole time, and the temperature control is relatively imprecise, because the only thing you can vary is the temperature of the air going into a zone. A variable air volume system is more expensive and complicated, but it's more efficient and provides more precise temperature control. This is because, in addition to changing the temperature of the air going into a zone, you can also change the amount of air going into the zone. And because the fans don't have to operate at maximum speed the whole time, it is more efficient. There's 2 types of boilers, condensing and non-condensing. A condensing boiler is more efficient. It's 91% or more efficient usually, but it does have a higher initial cost. A non-condensing boiler is less efficient at around 80%, but has a lower initial cost. I ran a cost analysis on the 2 types of boilers, and a condensing boiler is about $280 cheaper per year for fuel prices. Over the 25-year lifespan of a boiler, this amounts to about $4,500, which would more than make up for the initial cost of the more expensive condensing boiler. The 6 and 12 south-facing windows was also analyzed. Sunlight is better than artificial light, and 12 windows would provide more sunlight than 6. More sunlight also means less light usage, which would be cheaper electrically. More windows does increase heating and cooling loads. Over the course of a year, it would add $78 to the yearly heating and cooling bill and 1.5 tons in peak cooling loads. The recommended design for this system is a single duct VAV system with 7 heating and cooling zones. The cooling is provided by a direct expansion unit, and the bathroom air is supplied via door vents. This just pulls air to the bathrooms from the open office space. The hot water system will use a condensing boiler. The distribution system will use a primary, secondary loop, and reverse return. All the hot water pumps will be fitted with variable flow devices, and the circulation pump will have a redundant pump in case of failure. The bathrooms in the entryway will be heated with fin tube, and the maintenance room will be heated with a hydronic unit heater. I also decided to go with 12 south-facing windows for the increased daylighting. To explain a VAV system, I've included a detail of a VAV terminal unit. The terminal unit is what controls the temperature of the air and the amount of air going to a zone. Air comes from the air handling unit at 55 degrees, and then the volume of air is changed by a damper inside the VAV box. The air can then be heated by a hot water coil, so the air can be changed from 55 degrees all the way up to 90 degrees if max heating is needed. I've also included a flow diagram to explain the primary-secondary loop. The boiler is on a separate loop so that not all the hot water has to run through the boiler. It can bypass the boiler if it doesn't need to be heated very much. You can also see the two pumps for the circulating system. In case one of the hot water pumps fails, the other one can run instead. And then the isolation valves can be closed and the pump can be removed for replacement or repair. This detail shows how the solar wall is connected to the air handling unit. The solar wall is connected in parallel with economizer cooling air. Economizer air is just plain outside air at outside air temperatures. This is mixed with the solar wall air so that a constant temperature can be provided to the air handling unit. If just solar wall air was used, it would be too hot. The air is then also mixed with return air from the building to provide a constant temperature for the air handling unit. This is set at 50 degrees and then is heated with the hot water coil in the air handling unit to 55 degrees for output. The DX coil can also be seen, which is used to cool the air down to 55 degrees if the intake air is too hot. This is the piping and ducting layout for the whole building. You can see all the zones that are provided by VAV boxes, which are the private offices, the break room, and then 2 VAV boxes service the large open office area. The environmental and societal impacts of this building have been minimized. The system has been made as efficient as possible to reduce the carbon footprint. Since this is a new construction, the public won't be affected or hindered by this installation. It's all going to be inside the building, so nothing outside will need to be shut down. The VAV system provides better temperature control, which in turn provides more comfort to the building occupants, and the larger number of south-facing windows provides better quality of light and more light to the occupants as well. Several options were used to improve the sustainability of this building. The variable air volume system is more efficient because the variable speed fan can reduce during non-peak operation. This saves on electricity costs, and also running the fan at lower speeds increases motor life. The pumps have also been fitted with variable frequency drives, so their speed can be reduced to save electricity. The lower pump speed increases pump life as well. The condensing boiler was also selected because it has reduced natural gas consumption. This decreases the carbon footprint of the building. The solar wall also provides a substantial amount of preheated air. This should allow the boiler to not have to run nearly as often as it would if the solar wall wasn't there. The cost estimate for this building has been broken into multiple sections: water side, air side, balancing, and controls. The water side includes the boiler and all its components. The air side is the air handling unit, the ductwork, and all of its components. And then balancing is for people to come in and set all the pressures and the flow rates for both the hot water and the air system. The controls are all the electronics required to make the entire system work. The subtotal for this is $374,000, and an additional 10% contingency and 5% for permits and bonds brings the grand total to $430,000. These are my code and data references, and I would also like to thank my project sponsor, Christopher Batson, and thank you for watching this presentation.